I'm going to do a series to the best of my ability on the primitives in the BRC100 wallet toolbox. I did a previous video not long ago on the SPV wallet installation, and it turns out the devs are being moved towards all of the BRC100 primitives. Now, I'm one that likes to know the parts before I jump into the all. So I'm going to go through the primitives in the BRC100 toolbox by a lot of times building little applications. And in this case, it looks to be about 29 methods or so, plus give or take. And this application I'm going to show you has 4 of those methods. And the 4 methods are sign, encrypt, decrypt, and verify signature. I don't know if it's exactly called that, but those are the 4 methods from the BRC100 toolbox that I'm going to show you. And I'm going to show you 2 ways. And it is encrypted messaging primitives, a builder's walkthrough of the cryptography. So the application is a secure peer-to-peer messaging app. All of those words are important. Secure meaning we encrypt it. Peer-to-peer meaning the 2 people that are involved are computing keys with each other. And that is the peer-to-peer thing in BRC100. And this is going to go through the crypto. And by crypto, I mean the cryptography. So what is used is ECDH, key derivation, and then the AES encryption. A lot of this, so when I built this little application, I installed the TypeScript BRC100 wallet library, and I installed BSV SDK. That wallet library uses a lot of things in the SDK. So first thing we're going to see, Alice is set up. So Alice sends, the command is send, and you'll see that. And then there is an invoice number, and this is important for computing those shared keys. If you're familiar with the BRC terminology, this is where BRC43 comes in. So the method we'll call is wallet.encrypt. So it is a method on the wallet object. And let's see here. Yeah, so this is the ECDH. So ECDH, very simply, is that my private key and Bob's public key are equal to Bob's private key and my public key. That's ECDH right there. But we add in that invoice number so that we can do fun things together, like compute keys on the fly. All right, so you can look through this. You can stop the video, and this will show you that math if you want to go through it. Next thing is, in the Alice send world, is encryption. We also use that ECDH derived key methodology. So she's going to be using, for both of those operations, she's going to be using Bob's public key. And what she's getting here is a key that she's going to use in the AES encryption algorithm. The envelope is what gets sent to Bob. And what's contained in the envelope is Alice's identity key. So Bob knows who's sending it to him. And she gives him the key ID. She gives him the ciphertext, and she gives him the signature. Now, people that are familiar with BRC 43 will see that why isn't there a protocol and security level? And that's because the security level is going to be 2 for this application that I wrote, always. The key ID is here, and then the protocol is the secure messaging app. I can't remember what I called it, but this application knows its protocol and it knows its security level. All it needs is a key ID that's incremented every message that gets sent. So, and then this envelope is what gets sent to Bob. Now, Bob runs receive. And like I said, Bob knows that it's security level 2, and he knows that the protocol is encrypted message, and he receives this 001 key ID from Alice. He does the same crypto math, and he gets the same shared secret. And he uses that shared secret with the invoice number up here, same invoice number that Alice used. And he gets the information that he needs to verify the signature. So now he's going to decrypt. And again, he is going to compute a key on the fly that uses Alice's public key. So both sides derive the same symmetric key independently. No shared secret is ever transmitted over the wire. No keys, nothing. The invoice number makes each conversation uniquely keyed. And so that's why you would increment that key each time. So that's that. We might come back to that. But now I thought I would take us over to the terminal. And I have already initialized this application, which created a seed, a private key for each of them. So we're going to do yes, node. Let's run identity so you can see the key. Whoops. What did I forget? I forgot to name the application. That's the command. The application is called secure messaging.ts. This is in TypeScript. So now we got Alice's public key there. Okay. And now we are going to do the same thing over here. npx ts node secure messaging.ts. All right, and there is Bob's public key. So I just copied that onto my clipboard. I'm going to clear the terminal here. And now the command I'm going to run from this little application that I wrote is called send. So Alice looks up in a directory Bob's key. And Alice says, send, and then she types in Bob's key. And then she types a message. Hi, Bob. This is a super secret message. And we end that quote. When I press enter, we're going to be running 2 methods. And the two methods were first encrypt and then sign. So, and we got, so it has to put who she is in here so that Bob knows who's sending it. It puts the key ID, which is 001, and then it puts the ciphertext. So now we will copy this blob. And you might ask, why do we have to send a signature? Because if you understand the crypto going on, you know that to decrypt, you don't need a signature. But the reason why we put it in is that someone could intercept this, put their own public key in here, and say that they sent it. So we're going to add a signature in there so that Bob can verify that it in fact was from his friend Alice. So now we're over here on Bob's terminal and we are going to run receive. Let's see, do we have, yep. We're going to run receive and we are going to put in this blob. I think I have everything. Running two methods. The methods are decrypt and verify signature. And so you can see that it knows that it received a message from Alice. And Alice's signature was true. And it says, "Hi, Bob, this is a super secret message." So it all worked. So now we can we'll send a quick one back. We'll say send. And we need to get Alice's key. And I think I had it over there too, didn't I? Yes. But let's just grab it. We're going to send to my friend Alice. And we are going to say, hi back. All right. Again, we ran the two methods. What do we do? We encrypted and then we signed. And we did all of the crypto math that computed derived keys by taking Alice's public key with Bob's private key and doing that crypto math to get the signature and the secure encryption. And so one thing to note here is in this application, and I do have the code up on GitHub, I use this same key for both encryption and sending. In practice, you would probably not do that. You would probably do separate keys for each thing. But anyway, let's pop back here. And we are going to do, what are we going to do? We are going to receive over on Alice's end. And let's put our blob in and put quotes around it. There you go. We checked the signature. It's valid. And we got the message that said hi back. So I don't know if we need to go back to this guy. All right. So let's see if there's anything else in here we want to look at now that we've ran through that. So basically what this does is this more shows you the math for each of the methods. One thing I also want to say here is that what we're seeing here is, the basic math here is what things that Signal uses. Okay, they use a Diffie-Hellman type algorithm, DH, the ECDH. They use a type of that algorithm, and they, with me, when I send you a message on Signal, it's doing that behind the scenes. So what's cool about all this is that it's contained with the BRC100 paradigm. And so that identity that you have, that's your seed, that is a whole nother story that we'll talk about another time, because that needs to be very secure. And there are people building things that will do that for us. But what I wanted to say is that this application is like, if you're a cryptography nerd, which I wasn't until about a year ago, or you would know what all this is. It would be like, oh yeah, so what? Well, the so what is that it's in the BRC100 paradigm, and that seed and the identity key that's doing right now signing and encrypting messages, then we can build on that and do a lot more things, like manage our certificates, which are NFTs, perhaps stream media. And these all can be different keys and different, protocols. So anyway, I hope this was helpful, and I will put the link to the GitHub if you want to look at the code and maybe run something like this yourself. This is not production code, and I did make sure to put that in the comment that you would not want to put something like this in production. But it will teach you how all of this works. So that's all.
Got a curve in the game, laid out clean, with the point named G and a math machine. Pick a secret number, that's your key. Multiply G, now the public can see. On the curve, can't fake what you saw.